because losing electrons is oxidation. And then the reduction half is going to have electrons in the reactants. Yeah, can I just wait? I'll show you exactly what I mean when we do an example. It's going to be way easier to see that. So in step 5, what we've done is we already had the equation balanced with atoms. Now it's going to be balanced in charge too. So you're going to have 2 half reactions, one oxidation, one reduction. They're totally balanced. Now it's time to start thinking about putting them back together to make one overall chemical equation. One last thing before we can do that, though, and that is the number of electrons given off by the oxidation must equal the number taken in. You can't give off 1 electron and then take in 10. If you're going to take in 10, that means you need to give off 10. So because oxidation and reduction happen simultaneously, they have to give off the same number as are taken in. So we're going to have to use some multiple of each half reaction to get the number of electrons equal. And once again, I'll show you what I mean by that.
Are we getting the worksheet today?
It's on Schoology. Yeah.
Wait, is this just balancing? Like,
It's just balancing. All we're doing is balancing.
It's hard.
It's not really even hard. You just need practice at it. It's not. Doesn't turn out to be terrible. People generally do really well on this.
There's a worksheet.
Yeah, there's a worksheet on Schoology. It's got 14 redox equations to balance. One of those 14 will be on the quiz on Friday.
Not word for word.
Yes, this one will be word for word, and the solutions are given on that worksheet too. So I'll show you. I'll show you. We'll see that at the end of the hour. Okay, so now I'll just get rid of this shade, maybe. Now that the number of electrons will be made equal, now we can add those two together. The electrons are going to cancel out, and we'll have one balanced net ionic equation. And then after that, if there are spectator ions, or if there were spectator ions that were given to us, we'll add those back in too. So this will make much more sense when you see it done. And I'm hoping, in the amount of time we have left, that we can do 2 examples. And you'll see how very systematic this is. Ready? Everybody good with that? Writing all that? Okay.
Wait, we need like more than one paper for this.
How much room do you have?
We need a lot of paper.
You need a couple lines for these.
Is there a negative next to the BR?
It is. It's small. Yeah. It's BR negative. Yep.
Wait, do you care about the states?
Not right now, no, because we know this is just an ionic equation. When you have the full equation, though, the states will matter. And we'll see the full molecular equation.
Is that like other quizzes we have to write the states on?
No.
Oh.
No. I find it's helpful because there's so many steps to use different colors for the various steps. If you have a set of colored pencils, you might want to, if you look back at your notes and you realize what you're doing each step, that may be helpful. So I'm going to try to do that. I've got the convenience of the markers here. The markers we can make all different colors. I'll try to use a different color for each step. So the first thing that we have to do, though, is identify who gets oxidized and who gets reduced. Before we can even write 2 half reactions, we'll go back to what we did on Friday. So Br negative, that's what we consider a monatomic ion. It's got a -1 charge, therefore a -1 oxidation number. MnO4 is the permanganate ion. O is -2. the whole thing adds up to -1, right? That's the charge of the permanganate. What is the Mn's oxidation number?
7.
It's 7, right? Positive 7. What we do here is we say, okay, what does Mn have to be so that when you add it to -8, you get -1? That's how we came up with
Wait,
negative
how's
7.
that real?
Elements by themselves are just 0.
Yeah, that's what I'm thinking.
Oh.
No, an element like this would be an element by itself, where it's just an element that has nothing attached to it.
Wait, so does that
ER
mean?
not attached to
Yeah.
it?
No, but that's an ion. As you see, it's hard to see, but there's a negative sign there. So the bromide ion has been separated from its counter ion. Some positive ion is there, but it's a spectator. Okay. So yeah, the Br2 is 0. It's just like the Fe in the steel wool was just 0 initially, until it reacted. Then the Mn is positive 2, so that's its oxidation number. In this reaction, something oxidizes and something reduces. The thing that goes up in oxidation number oxidizes. The thing that goes down reduces.
And then reduces.
Yep. Yep. This is our reduction. You don't have to write this on your paper, but just for our, organization. And then the Br is -1. It goes up to 0. That oxidizes.
What happens to that oxygen? Does that become 4H2O?
Yes. Yeah, that's what we're going to see. Yep. Okay, so here's what I want you to do. To write 2 separate half reactions. On the left side of your paper, write ox and red.
Is this called still the first step?
Yeah, now we're starting the first step. So, don't write anything directly next to the ox and red. We'll have to fill those in a little bit. So in the middle of your paper, the oxidation half reaction is going to be the thing that oxidizes, which the Br negative changes to Br2. That would be the oxidation half reaction. So remember, there's always oxidation and reduction. There's never just one and not the other. So there's our oxidation half reaction. The reduction half reaction is the manganese changing from positive 7 down to positive 2. Now listen to this. When the manganese is attached to the oxygen initially, you need to keep the oxygen with it. Don't just put Mn plus 7 yields Mn plus 2. It was part of a polyatomic ion. That oxygen was attached to the manganese at the beginning, so it needs to stay on there for now. So there's our reactant. Even though the oxygen didn't really change, I mean it left the manganese, but it didn't change its oxidation number. It was still part of that unit. So this would be the reduction half reaction. Yeah, no.
Why are we not adding that 4H2O? in that?
Oh, we will. That's step 4, I think. We're
Is that still
step
part of the second half reaction?
Yeah. So now we start balancing the half reactions. Yep, we will. So there's our 2 half reactions. We have what oxidizes and what reduces. Now we start to balance. Step 1 is, step 2 now. Balance the non-hydrogen and oxygen atoms. So we do that. We have 2 Brs on the right there, but only 1 Br on the left. So with a different color, I'll use the red. I'll put a 2 in front of that, so that takes care of balancing the Brs. Now with this reduction half reaction, there's 1 Mn there and 1 Mn there, so we don't have to do anything with it. So that takes care of step 2. Step 3, we balance the oxygens next. We don't have to worry about that in the oxidation half because there is no oxygen. But now, we're going to scratch your itch. We have 4 oxygens on the left. We can put the 4 water molecules on the right now. Different color. I'll pick up my green. So yeah, 4 oxygens are removed from the Mn. They're going to show up at the end. Because this thing is an acid, we know that the oxygen is going to show up in the form of water molecules. So that takes care of balancing the oxygen. Yes?
What about that hydrogen? Isn't it not an equal equation there though?
Yeah, let's look at that.
Because
Yeah, where the hydrogen comes from. Remember, this was an acid, so now we have to account for the hydrogens. That's why I have you do it in that order. I have you doing the oxygens first, because I know water's going to get thrown in here. Now that introduces hydrogens, we have to do those last. Okay? So, again, in the oxidation half, there is no hydrogen, so we don't worry about it. In the bottom half, we have 8 hydrogens on the right. Now with a different color, I'll come back here and add 8 hydrogens to the left to account for the hydrogens. And now at this point, both half reactions are balanced. They have the same number of atoms on both sides. However, they're not balanced for charge. The oxidation gave off electrons. We need to account for the charge as well as the atoms. So, okay, this is where now, I've exhausted my 4 colors. I'll go to something different. I think orange turns out to be a nice color. Let's use that. Oxidation. The definition of oxidation is the loss of electrons. So that means that in the oxidation half, every single time you write an oxidation half reaction, electrons are going to be a product. Electrons will never be a reactant for an oxidation. That's not what oxidation is. It's the loss of electrons, so they'll be given up. We'll fill that line in a moment. Now they'll be right there. In the reduction half, the electrons will be a reactant because reduction is the gain of electrons, so they have to come into the reaction and get used up. Go ahead.
So, would you not put the opposite then for a negative? So for like 2BR then, say you're going to add 2E on the left side, would you not put like subtract 2BR negative charge minus 2E?
Yeah, what's happening is this Br negative is losing electrons, but in a chemical equation we don't subtract. We just, if we're removing something from the reactants, then it shows up as a product. So you got 2 electrons that have been given off by the reaction. It's kind of the same thing as what you're saying, but instead of subtracting stuff, we just add it to the other side. Yep. So now check this out. The left side, the total charge is -2 because you got 2 -1 ions, right? On the right side, the Br2 is neutral. So what we do in this step is we make sure the total charge on the left equals the total charge on the right. If the left side is -2, I need to add electrons so that the right side is -2. How many electrons? 2 electrons. Yeah. Now, what that means is both sides have to be the same. They're not necessarily neutral. We're not necessarily trying to make both sides neutral. In fact, they're not neutral. This is -2. Now this is -2. That's what we want. We want them to be the same. In the second half, what I always do to figure out how many electrons I need to add, I look at the other side, the side that doesn't have the electrons in it. So the water is neutral. The right side is +2. So on the right side is +2. The left side, before I add any electrons to it, what is the charge of this?
0.
No?
Oh,
We've got 8 of these.
7.
+7. +7. Yeah, I heard that. Yeah, but you can see that. +8 and -1 is +7. So the right side is +2. The left side is +7. And I know I'm going to have to add electrons to the left side. So how many electrons would I add to +7 to bring it down to +2? 5. We need to add 5 electrons. Once again, I'll say that again. Yeah, just hang in there. Look at this. The right side is +2. That's neutral. That's +2.
Hey, what is the rule for H2O again? You said that it has a 0. I kind of forgot what the rule was.
No rule.
The reason the oxidation number is 0.
Oh, because it's a compound.
I do all
This is a compound, but that's not a compound. It's just an ion. So anytime you have a neutral compound, there's just no charge.
Oh, so compound.
Because it doesn't have a charge on it. Yeah, this thing is not neutral because I'm giving the charge. Yeah.
Compounds and elements all have 0.
Right, that's right. Compounds and elements will have 0 charge. They won't show an ion there. Yep. Okay, so the right side, neutral and +2 makes the right side +2. The left side, again, I'm going to cover up the electrons. Just look at this set of ions here. I got +8 and -1. That's a total of +7. That adds up to +7. So I know that this is reduction, and this is going to take in electrons. So I'm going to put in some number of electrons. How many? The how many is determined by when you see that this side is +2, this side without that is +7. How many electrons do I need to add to +7 to bring the charge down to what it is over there? So that side was 2. I need to have that 7 and add 5 electrons to it to bring that 7 down to a 2. The left side and the right side have to have the same total charge. Now remember, the whole idea of oxidation and reduction is something is happening with electrons. So either electrons are given off or electrons are taken in. Oxidation is when electrons are given off. So we know that the electrons will be in the products. Reduction is where electrons are taken in. So we know in the reduction half the electrons are going to be in the reactant.
What's that?
Almost there.
No, no.